the number of strings of length 7 which begin with 5 consecutive ones, then that's pretty easy because the first 5 have to be ones, and then once you make the first 5 characters ones, then you're free to let the final 2 characters be whatever you want. This could be a 0 or a 1, and this could be a 0 or a 1. So there are precisely 4 strings which have this property, 4 strings of length 7 which have the property that the first 5 characters are ones. But we want to know the number of strings which meet any one of these 3 properties. So there are going to be 4. Well, let me just sort of finish the formalism. So let's let this A equals is a little bit confusing. So I'll just sort of write A colon or something like that, and I'll actually just use the letter A. Let A equal. I define A combinatorially as the number of strings with 5 starting ones. 5 starting ones. And of course, it's true that A is 4. Or maybe I want to let A be the set of strings, just to match my old notation. So let A be the set of strings with 5 consecutive ones, and let B be the set of strings with 5 middle ones, and let C be the set of strings with 5 final ones. Okay, and like I was saying, it's easy to see that each of these sets is of size 4. But it's not true that there are, but what are we trying to count? We're trying to find the strings of length 7 which have a sequence of 5 consecutive ones, and so we want all the strings that are either in this set or in this set or in this set. But of course you can have a string which is in multiple ones of these sets. And so if you're not very careful, you can overcount the situation by forgetting that the string 1 1 1 1 1 0, or sorry, 1 1 1 1 1 1 0, for example, is is in A because it starts with 5 ones, but also in B. Let me just write that down really fast. 1 1 1 1 1. So that's the first 5. 1 0 does begin with 5 consecutive ones, but it also has 5 middle ones. And so it's a member of set A, but also a member of set B. And yet, if I'm trying to answer this question, I need to only count that string once. All right, so how do we do this carefully? The answer to this problem is, once we've set it up this way, is that this is going to be 2 to the 7th, so the total number of strings, minus all the strings which are in A or B or C. In other words, A union B union C, the size of that set. Okay? And now I apply inclusion exclusion to that. And this will be the size of A, the size of B, the size of C, minus the size of A intersect B, cha-cha, minus A intersect C, minus B intersect C, plus A intersect B intersect C, cha-cha, cha-cha-cha. Okay, this is surely correct. This is that's inclusion exclusion just stated out. So now we're just going to do all these. So let's go. Well, here we said already that this is 4, and that this is 4, and that this is 4. For example, there are clearly 4 strings that end in 5 final ones, because once I determine that the 5 final characters are ones, then these 2 characters are free to be whatever they want, and so 2 choices for the first character and 2 choices for the second character. Okay, so now, just doing this in our heads, how many strings are have both of these properties? What have I done? Oh no, that's the next problem. Good. How many strings have both of these properties? So what does it mean to be in set A intersect B? It means that you begin with 5 ones, and you have 5 middle ones. Well, if you begin with 5 ones and you have 5 middle ones, then, all right, doing some scratch work kind of over here, then what can we say? We can say that, in fact, you begin with 5 ones, so boom, but also the ones in the middle are all ones, and so the only thing left is what's over here. But in fact, there are 2 strings that are in both A and B. The string which ends in a 0 and the string that ends in a 1, because only the final character is free. So that's -2. Okay? How many strings are in A intersect C? Well, now you have to begin with 5 ones, but also end in 5 ones. Well, if you begin with 5 ones and also end in 5 ones, then the only possibility is that they're all ones. So there's only one string which is in both of those. Am I doing this right? Yeah. How about if your string ends in 5 ones, sorry, 5 middle ones and ends in 5 ones? Well, the only way for that to be true is if the 5 ones, the 5 characters in the middle are ones, and also the last 5 are ones. So now you're free only to choose what's in the first character, and there you have 2 choices. So here, what's sort of going on here, the big picture is I'm free, I'm using the inclusion-exclusion principle to sort of do my logic in a kind of a global way, so now I don't have to worry about all these, the undercounting and overcounting while I think through. It's quite nice here. I think this is the good way to do it. Okay, and finally, what does it mean to both start with 5 ones and have 5 middle ones and end with 5 ones? Well, there's only one bit string of length 7 that meets that property. It's the one in which they're all ones. And so this tells me that I can just do this, man. And so what do I get? 12 minus 5 is 7, and 1 is 8. And so I get 2 to the 7th minus 8, so that's 128 minus 8, so that's 120. So there must be 120 bit strings which don't, or rather, I guess the way to put it into words, that there are 8-bit strings that either begin with 5 ones, have 5 middle ones, or end with 5 ones. And since there are 128 total bit strings of length 7, then 120 of them don't have that property. Okay, I think this is really the way to do this problem. Alright, good. That was like a warm-up to 21, which is so hard, but is basically the same kind of problem. But I don't know, personally, I find this to be very hard, and I am happy to write things out slowly and carefully and tediously, because I think if I skipped steps, I would get the wrong answer. Although, perhaps if you're very smart, you can do this informally without screwing up. What does 20 say? That was 20. What does 21 say? 21 says, calculate the number of bit strings of length 9 that either begin with 2 zeros, have 8 consecutive zeros, or end with a 1. I'll write that down. I want the number of bit strings of length 9 that either begin with 2 zeros, have 8 consecutive zeros, or end with a 1 bit. Okay. Yikes. Well, it seems that based on our previous analysis, we should divide these 3 sets up into 3 different properties. So, consider property, or consider the first property, the property of beginning with 2 zeros. Well, this is a string of like 9 now, so 1, 2, 3, 4, 5, 6, 7, 8. That sucks. Try that again. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, and what do we know? It starts with 2 zeros. Okay, what's B? B are that there are 8 consecutive zeros. Okay, I don't even know how to write that, so I'm just going to write 8 consecutive zeros are in there somewhere. and property C is that it ends in a 1. So 1, 2, 3, 4, 5, 6, 7, 8, 9. There's a 1 here. Okay, so I will in fact let A be the set of strings with that property. So the set of strings of length 9 starting with 2 zeros. Starting with 2 zeros. And let B be the set of strings.
Soccer ball up here?
No.
Are you sure? Where is it?
The soccer ball is probably in a room somewhere. The set of strings with 8 consecutive zeros. And let C be the set of strings ending in a 1. Ending in a 1. Okay, and now note that the very thing being asked is the number of strings of length 9 that begin with 2 zeros, have 8 consecutive zeros, or end with a 1. So we want to know the number of strings that meet at least one of these properties. In other words, I want to know the number of strings in the union of these 3 sets of strings. Okay, so that's like quite clear now, I think, that this, given this notation, that this is what I want. And man, that's hard to do informally. So we're going to do it formally using inclusion exclusion. So what do we have? We have A, this is A plus B plus C minus A intersect B, I'm getting good at this now, minus A intersect C minus B intersect C plus A intersect B intersect C. Okay, and now this is the hard part is knowing how to start, but also now to do all these. All right, let's go. Well, how many strings are in set A? It's quite straightforward. The first 2 have to be zeros, and so there must be, we're essentially asked how many ways there are to finish off this string. For every character, it can be either 0 or 1. I have 7 choices, so this is 2 to the 7th. Okay, how many strings are in B? All right, well now I have to just like do almost another inclusion exclusion like inside this case, but I'm just going to do it out loud. How many strings are there with 8 consecutive zeros? Well, I claim there must be 3. Either the first 8 characters are zeros, and or I guess I should say bits. The first 8 bits are zeros, and the final bit is a 1. Or the first bit is a 1, and the final 8 are zeros. Or they're just all zeros. Those are just the only 3 ways to have 8 consecutive bits be zeros in a string of length 9. So, okay, boom, we just did that one out by brute force, I guess. How many strings are there that end in a 1? Well, if it ends in a 1, then the other 8 characters are free, and so there's going to be 2 to the 8th of these. Okay, now it starts to get a little bit harder. How many strings are there which are in A intersect B? Okay, so now I need to talk about a string which has the following 2 properties. It starts with 2 zeros, but also there are 8 consecutive zeros. Well, there's only one possible string. No, shit. Starts with 2 zeros, and there are 8 consecutive zeros. There are 2 strings that meet this condition. All zeros up until the last character, which is a 1. That's certainly in A and also in B, or just all zeros. Yeah. Okay, so there are 2 strings in this set. What about the set A intersect C? Okay, now it has this property and this property. So it starts with 2 zeros, but also it ends with a 1. Okay, that's easy. 3 of the 9 bits are accounted for, so I have only 6 choices in the middle. So that's 2 to the 6th choices. Okay, B intersect C. Well, now I think I got this. Now I think there really is only one of these. Because if you have 8 consecutive zeros but also end in a 1, then the only possible way for that to happen is if it's all 8 zeros and then followed by a 1. And finally, how many ways are there to have all 3 properties? The only way to have all 3 properties is to have 8 zeros and then end in a 1. Okay, so filling out these individual pieces I think was a little bit challenging, but now we're just done, right? So that's 128 plus 3 plus, really? Oh yeah, plus 256 minus 2 minus 64 minus 1 plus 1. And when you do all that out, am I doing this right? Mm-hmm. When you do all that out, you just get 321. And so there are 321 bit strings, a blank 9, that either begin with 2 zeros, have 8 consecutive zeros somewhere, or end with a 1 bit. Okay, good. 2 more problems to go, which are relatively easy maybe, and then we're done with this. Okay. Okay. Yeah, here we go. 22. How many 22. How many integers in the set 1 to 1000, I don't know what kind of notation that is, kind of weird, are divisible by at least one of the primes 2, 3, 5, 7. I will rewrite his notation to the way he normally does it. Are divisible by 2, 3, 5, or 7? Question mark. Alright, this problem's like a kind of a tedium, but it would be sad if we got to this unit and we never did inclusion exclusion with 4 sets. So the time to do that is now. Let's let A be the set of all numbers that are divisible by 2. Let B be the set of numbers that are divisible by 3. Let C be the set of numbers that are divisible by 5. And let's let D be the set of numbers that are divisible by 7. And then we just simply count them all. So what is I want to know all the how many integers are divisible by 2, 3, 5, or 7. So I want to know every number which either is in set A, or in set B, or in set C, or in set D. And this is going to be A plus B plus C plus D minus A intersect B minus A. Oh no, this is just going to continue on. Let's see, can we do this organized fashion or not? Yeah, let's do that. Okay, so then minus, and now we're going to have like 6 of these. Oh boy. A intersect B minus A intersect C minus A intersect D minus B intersect C minus B intersect D minus C intersect D. So these are all the numbers that are divisible by 2, all the numbers divisible by 3, all the numbers divisible by 5, all the numbers divisible by 7, all the numbers that are divisible by 2 and 3. We subtract those out because we double counted them. All the numbers that are divisible by 2 and 5, etc. Okay, and then we have to add back in all the numbers which we double subtracted. So that's A intersect B intersect C plus A intersect B intersect D. How's that look on camera? Probably bad. Stupid board. Plus B intersect C intersect D, I guess. That's all the 3 triples. Not the D, not the C, not the A. And finally, we subtract all the numbers which are in all of them. Okay, sorry, I meant to leave some space. Now you just stop and move on with disgust, or you just, tediously compute these. Of course, we'll do that second one. How many numbers are divisible by 2 out of 1,000? Well, Just 500 of them. Okay, that was easy. How many numbers are divisible by 3? Well, I think I'm pretty good with that, because 1,000 isn't, but 999 is. So it's going to be 999 divided by 3. So it's 333. How many numbers are divisible by 5? Well, 5 is a factor of 1,000, so I can just divide by 5 and I get 200. How many numbers are divisible by 7? That's a little harder for me, but I have on my side of my paper calculated that this is 142. So you just do 1,000 divided by 7, man, and you just get 1, 3. That goes in 4 times 28, 2, 0, and that's 2. So 142 with some sort of remainder. So that means that the last number that is divisible by 1,000 is actually what have I done? 980? Is that true? Is 980 divisible by 7? Of course it is, because 980 is just like 10 times 98, which is 49 times 2. So 980, 7 divides 980, and in fact 980 divided by 7 is 142, and none of the numbers between 981 and 1,000 are in. Okay, this is stupid, so now we just keep on going. How many numbers are, the rest of these I did in my head? I might have just, I don't know how I did the rest of these. A intersect B, so now we just want to know how many numbers are divisible by 6. 999 is not even, so we have to go to 996. So 996 divided by 6 is something. Apparently it's 166. Wait, I think I can do something kind of smart now. Well, I guess it's just subtract 1 off this and divide by 2. I don't remember how I got these numbers. I might have just done a calculator at this point out of disgust. How many numbers are a multiple of 2 and 5? Well, that's just numbers which are multiples of 10, so that's just 1,000, or 100. I guess the fast way, if you have a calculator, of getting 166, or even if you don't have a calculator, is just recognizing that we're finding the numbers which are divisible by 6. So you just do the same thing, right? You just do 1,000 divided by 6, and then you just kind of floor it, right? You just truncate the remainder. So whatever that is, and the answer is 36, and then it's just 4, so that's just 6, so it's 166. Yeah, so that's what you do. You just take the floor of the division of 1,000 divided by 6. This one is 71 according to my paper, so that's just 1,000 divided by 14. Take the floor of it. This is 1,000 divided by, what the hell's going on here? B intersect C. These are the numbers which are divisible by 15. So 15 goes into 1,000. This can't be right. 66 times? Oh yeah, sure, that could be right. B intersect D, so that means divisible by 3 and 7, so it's 1,000 divided by 21. Take the floor, that's 47. 1,000 divided by 35. Take the floor, that's 28. Okay, now I want all the numbers which are divisible by 2, 3, and 5, so that's 30. 1,000 divided by 30. Take the floor is 33. This is going to be 1,000 divided by 42. Take the floor is what have I done? A, B, C, A. Am I just so dumb that I forgot a whole 4 choose. Hold on. Oh my god. Okay, hold on. This is 4 choose 2. This is 4 choose 3, which is obviously 4. So I did it both wrong on my paper and wrong on my doing it live. So that's double embarrassing, and Barely caught it. Yeah, okay. This is the one, this is the set that doesn't have D. This is the one without C. This is the one, then there's the one without B, of course. A intersect C intersect D. And then there's the one without A, which is B intersect C intersect D. Okay, I'm sorry for those of you who are screaming in pain at this error. I did catch it though. So now I have no idea whether these numbers are right. This one is, according to my paper, which I now distrust, 14. And this, according to my paper, is 23. And this is 2 times 5 times 7 is 70. 1,000 divided by 70. That should be something I can do. 100, that's 100 divided by 7. So that's like whatever it is, right? 98. So it's 14. I guess this is also 14. Who knows anymore, man? So these numbers might be wrong, so I'll just kind of stop then, I guess. But this, and then this is 4. And then you crank it all out, and you get something, which I'm not going to write down the answer because I don't know it. Alright, that was terrible. Final problem! 24 says, hey, apply the Euler-Toschen function, which we learned about in the previous video. This problem is super tedious. I'm not going to actually do what it says. It just says calculate phi of n for a bunch of numbers. So what's phi of 16? Note that 16 is just 2 to the 4th. And so we want to know the numbers that are not relatively prime to 16 means that the numbers which are odd, basically. Okay, so this is just going to be 8. But the way to do it is to write this as 16 times 1 minus a half, because the only prime factor of 16 is 2. And think of this as half. Think of the half as a number of numbers up to 16 which are divisible by 2, so 1 minus a half of the numbers which are not divisible by 2, and so that fraction of the numbers from 1 to 16 are not divisible by 2, and so this is just 8. Okay, this problem is also sort of not interesting. So 19 is in fact prime, so I guess this is just showing that the formula works. So you're supposed to do 19 times 1 minus 1 over 19. Well, of course, if 19 is prime, then 1/19th of the numbers between 1 and 19 are multiples of 19. Specifically, it's only 19. So that means 1 minus 1/19th, also known as 18/19ths, are not multiples of 19. So you're really doing 19 times 18/19ths. Well, of course, you get that there are 18, therefore, numbers which are not divisible by 19, so that are relatively prime to 19. Okay, it gets slightly more interesting when you try to compute like 28. What is 28? It's 4 times 7, so it's 2 squared times 7. So the only prime factors of 28 are 2 and 7, and so you want to know the number of numbers which are not multiples of 2 or 7. So you do 28 times 1 minus a half times 1 minus a seventh. Half of the numbers are up to 28 are multiples of 2. So 1 minus a half are the numbers which are not multiples of 2, and 1/7 of the numbers between up to 28 are multiples of 7. So that means 1 minus a seventh, or 6/7. Here, I'll just write it out. Half of the numbers are not multiples of 2, and 6/7 of the numbers are not multiples of 7. So if you multiply those all together, you get the numbers which are not multiples of 2 or 7, because of the numbers that are not multiples of 2, 6/7 of them are not multiples of 7 either. And then that's just like 12, right? It's like 3, 4, 12. Yep. Last one. Oh boy. 30, which is just 5 times 6. So that's 2 times 3 times 5. So that's going to be, according to the formula, 30 times 1 minus a half times 1 minus a third times 1 minus a fifth. And if you think about what that really means, it's 30 times the fraction of numbers up to 30 that are not multiples of 2, a half, times the fraction of numbers up to 30 that are not multiples of 3, 2/3, because 2/3 of those will not be multiples of 2 or 3, and of the numbers that are not multiples of 2 or 3, I multiply by 4/5 of those will not be multiples of 5, because 4/5 of numbers in general are not multiples of 5. And if you so therefore this should give the numbers which are not multiples of 2 or 3 or 5, and that is the numbers which are relatively prime to 230. Okay, this homework is over, this unit is over. If you watched all the way to the end of all these videos, wow. Could be better, could be worse. That's my new catchphrase. Okay, bye, and more videos coming.